Hello, everybody. Thank you very much for joining this session. Very happy to be here to present the International Renewable Energy Agency, IRENA's latest work on what we call model supply regions, which are based on Copernicus data and which serve to provide model-ready databases on the resources of variable renewables. And I'm going to show you the way that we've applied this principle for the African continent. So I'll start with a quick introduction of why and how we need to represent variable renewables in energy models, more specifically in capacity expansion planning models. Then I will talk about these model supply regions that we've developed for the African continent for solar, photovoltaic, and wind power. And then I have a few closing remarks at the end. So, but first, to introduce the concept, why do we need capacity expansion planning? What you see here is a graph with time on the horizontal axis, 2015 to 2040, and capacity, power generation capacity on the vertical axis. This graph comes from a 2021 report by IRENA on Eastern and Southern Africa. The stacked graph indicates the total existing as well as committed power generation capacity over the years. At first, it's increasing because new power plants are coming online. On the long term, it will decrease because older plants get decommissioned. And if we look at the peak demand, the red line, that one will continue to rise. So it's clear that existing and committed power generation capacity will generally not be enough to meet future demand. So there's a gap. We need new technologies, we need new power plants to close that gap. So what technologies are they going to be? Are they going to be coal, gas, nuclear, solar, wind? Well, for that, we use models that are based on cost optimization to pick the best technologies for closing this gap and reliably meet electricity demand. Variable renewables like solar and wind can be a part of the solution, but they need a specific representation because we need to take into account that the wind doesn't always blow, that the sun doesn't always shine. So how can we represent these best in cost optimization models to capture the full range of options? Now, luckily, we already have global databases on the, for example, daily and seasonal cycles of renewable resource potential, such as the Global Solar Atlas and the Global Wind Atlas. But this is not really model-ready data. We cannot just take all the pixels of a single country and put them in a capacity expansion model because it will be way too heavy. The other extreme would be to just take one single profile as representative for a single country, but countries can be big and the resource disparity within a country, as you see in the maps, can be vast. So you kind of need to find the middle way between them. For some other renewable types like hydropower, you can represent individual projects because each hydropower plant is different, has very specific characteristics. For solar PV and wind, that doesn't apply as much. It's rather necessary to have a representative sample of each country's overall potential in your model. So that's what we've tried to do by identifying for each country a subset of what we could deem the most attractive locations for the deployment of solar and wind power parks. Now, as a criterion for attractive, we've used the levelized cost of electricity that is to be expected, including the costs for grid expansion to connect remote sites. So there's a premium if you want to connect a really remote site that will increase the costs. So generally, the better the resource quality, the lower the LCOE, but the higher the distance from grid, the further away from the grid, the higher the additional costs for lines and for additional roads, so the higher the LCOE. We exclude any unsuitable and protected areas from consideration, and then we screen what is left over by LCOE to get an all Africa dataset of what we call model supply regions for solar and wind. Screening by LCOE means that we take, for example, the top 5% or the top 10% of lowest LCOE resources, so those that could break even with the lowest selling price. Okay, so what are the results that we've obtained from this? You can see here a schematic representation of, again, how this calculation process goes. So we start, in this case, for solar PV in Egypt with a country's resource potential. Then in the second step, we exclude areas that are deemed unsuitable. Then in step 3, we extract the screened potential. In step 4, we cut the dataset up into smaller regions that each represent the typical size of utility scale power generation. And in the last step, we then select the cheapest sites out of those. So we do that for solar, and we also do that for wind. Now, This is the result of the screened model supply regions across Africa. So we screened here up to 5% of a country's area, in yellow for solar PV and in green for wind. So for each country, what you see here are the most attractive locations for solar PV and wind power development according to our criteria. The cheapest locations in each country to develop these resources, spatial resolution based on the Global Solar Atlas and Global Wind Atlas, and temporal resolution hourly based on ECMWF ERA 5 analysis, which we bias corrected to the mean that we find in each MSR from the Global Solar Atlas and the Global Wind Atlas, respectively. In the latter case, through empirical quantile mapping to preserve viable shapes of wind speeds. And as I said, there's a limit to the size that an MSR can have, which is typical for utility scale power evacuation. So for each of these MSRs, we are able to provide a range of metadata, including but not limited to the diurnal profiles and the seasonal profiles. So just an example day here of diurnal profiles from the Met year 2018 and the seasonal profiles from the Met year 2018 for two example locations in Somalia and Kenya, former for solar, the latter for wind. And we're able to explore the balance between resource quality and grid distance. So I'll explain that. We already know that solar resources are spatially a lot less divergent than wind resources. This is generally quite well known. Now we find solar PV resources, solar PV MSRs, to be typically 5 to 6 times closer to the existing grid infrastructure than wind MSRs. Since these already represent the cheapest locations in each country, we can conclude, this is the example of Madagascar that I'm showing here, we can conclude that for solar PV, it is cheapest to stay close to the grid because the resources are not very spatially divergent. So why would you go far away from the grid? The only gain you would get from that in terms of exploiting better resources would be marginal. For wind power, that's not the case. For wind power, it makes economic sense to exploit excellent far from grid resources. And that has everything to do with the fact that wind power scales with wind speed to the power of 3. Whereas for solar PV, the relationship with irradiation is closer to linear. We can also show how the MSRs across the continent would differ in comparison based on their LCOE. So here, the darker the color, the lower the LCOE, and thus the more attractive the resource. And what we can see is that generally the most attractive locations for solar and wind power development are to be found in a region stretching roughly northwest to northeast to southwest, which I like to dub the African resource boomerang, for lack of a better word, and I hope it will catch on. We can also show how the LCOE, the expected LCOE, depends on the average capacity factor, in this case for solar PV. And each dot here represents a country, so the average across the MSRs in a certain country. And we can see that even though there is a very clear downward trend, higher capacity factor means better resources, means lower LCOE, that's logical, but there is considerable scatter in this graph. So for example, on the right-hand side, Somalia and Namibia have roughly the same average capacity factor, but quite different costs. And that is because the grid in Namibia is already much more developed than in Somalia. So you don't have as many additional costs for expanding the grid to connect a solar plant. Now, these numbers here are based on 2020 capital and operational expenses for solar PV and wind power. The numbers will shift in the future as these resources become cheaper. And as the price will drop by 2040, for example, we can expect roughly a 50% cost decline of these costs. MSRs for solar PV and for wind will shift somewhat closer to existing grid infrastructure with somewhat of a compromise in the average capacity factor. That effect is larger for wind than for solar power. This is logical because as it becomes cheaper to build the plants, it becomes more attractive to exploit the somewhat less attractive resources. What you can see here is a map of Ethiopia, in which we have clustered the MSRs into 10 different regions that result in very similar profiles, very similar production profiles on diurnal and seasonal timescales. And this is what we recommend as inclusion to energy models, to capacity expansion planning models. So instead of representing each separate MSR, which is still kind of like different pixels, we recommend representing them by different clusters that represent different regions as individual technologies. So in this case, for Ethiopia, the models that we use in IRENA have 10 technologies that represent the overall solar PV potential, each corresponding to one of the clusters. Depending on the size of the country, we reduce the number of clusters so that we reduce the overall runtime of the model. For Niger, for example, we tend to use 5 clusters. This is the example for wind potential in Niger. So just to close off here, in terms of general conclusions, the MSRs that we have developed in IRENA provide model-ready zones for solar PV and wind deployment to include in energy models as future investment options to close the gap between the capacity that is available for supply and the increasing power demand. It bridges the gap between highly detailed resource datasets on one hand and practical requirements for energy models on the other. All the MSRs can be provided to energy models as options. The selection which MSRs or which clusters will be chosen happens based on the cost optimization of the entire system. So the hourly and seasonal profile shapes can also play a role there. And this clustering method is very successful to reduce long run times. So let's remember, take home message. The strongest resources are not necessarily the cheapest, as our analysis from the previous slides shows. And the cheapest resources in the end will not necessarily be the most optimal, because the optimization happens from a system point of view. So temporal profiles also matter. Thank you very much.